Hello, this is the San Jose State Master's Project for the autonomous quadcopter, and this is a tutorial of our software project and development project. So here we have the quadcopter task. This is basically our free RTOS quadcopter task. This is responsible for processing sensor values and applying the flight controller inputs to the quadcopter. And so basically we have here like our init function, which is processed during init before the RTOS starts, and our run function. Our run function does many things. It processes sensor data, updates LEDs, performs calibration, and basically is like the control loop or the thread of the operating system. And here we have our quadcopter base. This is the manager, so to speak, which controls the flight controller class. So this class stabilizes a flight controller and is responsible for mainly the higher level control logic during flight. So here we basically have our GPS data. We're able to set and get GPS coordinates. We can check the altitude, check the battery percentage, and basically update our flying logic and apply the propeller values. And here in our quadcopter class, this is basically the interface to set the rotor PWMs. Here you can apply motor values, scale the motor values, and basically has the PWM outputs that would be set to each motor of the physical quadcopter. Here we have our PID class, and this is basically encapsulates all of the PID logics. So basically the gains or the coefficients for each proportion, integral, and derivative gain for each axis. So each axis has its own object or instance of a PID class, and that way it's like encapsulates all of the gains in one place. And drilling down back to some more tasks, we have another RC remote task. What this is responsible for is during manual mode, we have GPIO interrupts that trigger off of a remote control receiver. And so this task basically checks the duty cycle that it receives from the transmitter and calculates what is the throttle or what is the requested angle. And then at the end, it applies this to the flight controller angles of the quadcopter class. And drilling down to what we use a lot of our debugging time, we have quadcopter terminal commands. These terminal commands are accessible through serial terminal, and it allows us to get or set the PID gains for each axis, enable logging, calibrate the sensors, or even just set some angles or controls for the quadcopter to fly. And in our last major part of this project is our sensors class. What this was responsible for is encapsulating the sensor data, and these practice C++ polymorphism. So what we've done is we define them as pure virtual functions, and we have other classes that inherit from them, and that way all the interface is all the same for all the different types of sensors we use, but the operation is different once they're implemented in the code. So here I'm going to go and show you the serial terminal console that I was referring to. And here we have many different types of commands, as you can see. So here we're able to log, read and write to an SD card that is on the flight controller. And here we have a quad terminal command. And like I said, we have a logger, calibrate, so we can set quad, calibrate, and what it's doing right now is it's calibrating the sensors and resetting them to the sensor values to 0, so that right now the sensor angles are offset 0. And here other commands that we have are quad PID and get. So right now we have our PID gain coefficients here readily available, and we can basically read and write to NVRAM. And here, just to show you a demo, right now we have the quadcopter in manual mode, and so in manual mode we have control over the quadcopter from a remote control. And then right now, I'll go ahead and plug it in. So right now the quadcopter is disarmed. Once the ESCs are programmed and ready, you'll hear that double beep that we just saw. And now we can arm the system. And basically that was armed and dangerous video. And that concludes our demo of the software and project of the quadcopter.